from Caltech. And so there is a time difference that justifies the delay. The talk will be about information theory, so we will go back to our traditional topics next time. So let me take the opportunity to thank Antonino for having organized these events and to thank today's speaker that we are honored to have with us. Please, Antonino.
Good afternoon to everyone. It's a real pleasure to have with us today Professor Rino Rappuoli. Rino Rappuoli is the father and pioneer of modern vaccines, and he's a global established international leader in the field. He has pioneered the so-called reverse vaccinology, whereby vaccines are developed starting from the genome of the pathogen rather than from the pathogen itself. He is currently the scientific director of R&D at GSK Vaccines. He has had a very remarkable career. After his laurea in 1976 in biological sciences at the University of Siena, after visiting Harvard and Rockefeller, he came back to Centro Ricerca Sclavo in Siena, which was a major center for immunology and vaccines. And he became, in 1988, the director of the Centro Ricerca Sclavo. After Sclavo acquisition by Chiron Corporation, and after the acquisition of Chiron by Novartis, he kept climbing up the ladder of executive roles in becoming the global director of vaccine division of Novartis in 1996, directing laboratories in 3 continents and really a global enterprise. And since 2015, he's the director of R&D of vaccine division of GlaxoSmithKline. Professor Rappuoli has had a lifetime dedicated to vaccines and is having a lifetime dedicated to vaccines. He has been the pioneer of, and he has established many vaccines, the first recombinant vaccine against pertussis, vaccines against Haemophilus influenza B, hepatitis A, and very remarkably, the vaccines against meningococcus C and B. And we are all, the society is very grateful to Professor Rappuoli for his achievements. And he's a member of several prestigious academies, only to mention the National Academy of Science in the United States and the foreign member of the Royal Society in the UK. He has been the recipient of a number of very prestigious prizes and awards. I'd like only, few of them are nominated to immunologists that have made the history of immunology, the Paul Ehrlich and Ludwig Darmstädter in 1991, and recently the Robert Koch Award. In addition to this, I'd like to mention the gold medal to Albert Sabin, which is, of course, we all know Albert Sabin. And again, medals are nominated to prestigious immunologists, and he has been the recipient, and Premio Feltrinelli dell'Accademia dei Lincei. I like also to mention the gold medal for Al Merito della Sanità Pubblica. I like to mention this because the recognition of the role of his research for public health system by the President of the Republic. He was given this medal by President Azeglio Ciampi. Without any further ado, we really look forward. Thank you for giving this colloquium, Professor Rappuoli. And today he will talk about vaccines and monoclonal antibodies against this latest virus. And we look forward to your talk, and thank you again.
Well, thank you, Antonino. Thank you all. Good afternoon. It's a pleasure to be with you to talk about this pandemic today. Let me be patient for a moment. I'll start to share my screen, and then we'll start. Please tell me if you can see my screen. We always need
yes,
we can.
Confirmation. Perfect. Thank you very much. Now I'll set up the pointer, and then we can get going. I assume you see the pointer as well. So this is the title, Vaccines and Monoclonals to Regain Our Freedom. obviously, I will be talking about vaccines and monoclonals, and at the end, we'll discuss why that's important to gain our freedom. Now, I've been giving a lot of talks about pandemics, and not just during the last year. I started talking about pandemics since SARS in 2002. And since then, every time I talk about pandemics, I start with this slide. I'm sure all of you know Siena, and this is the view of Siena, the city where I live in Tuscany. And there is a reason I start with Siena to talk about pandemics. Because in Siena, I mean, the history of a pandemic has left a sign basically for centuries. And a couple of slides, I will tell you what happened in Siena and how that relevant that can be for today. In order to understand that, we need to go back to basically the end of 1200, in beginning of 1300. At that time, Siena in the 14th century was a very rich city. Can't believe it, but it was larger than Paris at that time, probably around 100,000 people, and was very rich. And the reason it was rich is because Siena is on the what we call Via Francigena, which is the road that basically links Rome to Northern Europe. And all people moving to Rome and going to Northern Europe had to stop in Siena. And the Sienese have been very good in setting up trade. They had built a hospital, places for people to stay, lending money, and basically they became very rich, and a very prosperous city. And like it often happens when the system is very rich, poets, architects, painters, whatever was at that time sculptures, people, artists, and people were really like to go there. And in fact, the Scuola Senese of painting, which started with basically Duccio di Boninsegna at the end of 1200, and Ambrogio Lorenzetti, Pietro Lorenzetti in 1300. And here you see one example of that. The School of Siena was one of the first school of paintings, one of the first sign of civilization after the Middle Age. So that was the atmosphere. People were rich, great culture, very flourishing society. So at that point, the Sienese decided they wanted to do something that should be remembered forever. And they decided to build the largest cathedral that was ever built. At that time, building the largest cathedral meant to show the power. Today, if you want to show how powerful and rich you are, you build the tallest building in the world. At that time was building a cathedral. So they had the money, they started, they had the architects, the painters, everybody, and they started building the cathedral. It was 1348. But then, some point, 1348, while they had just started building, the Black Death, the plague, arrived to Siena. It was May 1348. And in 3 months, by September, 2/3 of the population had died. The architects, the painters died. The city was not rich. And what is left of that is this wall. You see this wall indicated by a red arrow. This was supposed to be the facade of the cathedral. You see, it was supposed to go up like this, and this was watching south. The people coming from Rome were going to see this enormous cathedral, and you're going to be intimidated, saying, wow, look in what city you are going. But that dream never happened because the plague basically killed the people, stopped the economy, and basically the cathedral was built a couple of centuries later, but is much smaller, still beautiful, fantastic, but much smaller than the one that dreamed at the beginning. So what's the lesson from that? Well, this is the same wall we call facciatone, seen from the inside. All this was supposed to be the inside of the cathedral. And I go by this wall very often, and all the time I call this wall the largest monument to infectious diseases that's ever been built. And is a monument, is a wall that reminds us that an infectious disease can come anytime, no matter how rich you are, can come anytime, can destroy the economy, can kill people, and can change history forever. So that's what happened in Siena in 1348. Now, what's the lesson from us? What's the difference with the pandemic we are living right now? Well, I mean, for sure, we have a lot of deaths. This is taken from Manaus, Brazil, but even in Italy, I mean, we've got more than 100,000 deaths. So we do have a lot of deaths. And we also have an impact on the economy, huge. I mean, that's what we talk about every day. In the, I mean, the big calculations, what the impact on the economy has been so far, and people talk about $16 trillion already. Well, 16 trillion is basically the value of 1 year of the economy of the United States, the GDP. Is 10 years of value of the Italian economy. I mean, it's huge, and it's not over. It's going to be costing more. So what else can we say about the differences between 1348 and today? Well, if I look back at 2020, I mean, 2020 was not very different from 1348. I mean, the way we faced the pandemic was with the same tools that people from Siena had 7 centuries ago. I mean, the only thing we had to quarantine, social distancing, hygiene, what we call non-pharmaceutical interventions. Basically, it's exactly the same thing. I mean, 2020, that's what we had. The difference is happening in 2021. And the reason is that today we have science and technology, and during the 2020, basically the scientists have been working really hard to provide the tools that are going to help us to get out of this pandemic. Which are the tools? I mean, the tools that we already have are vaccines and human monoclonal antibodies. In the future, we will have antivirals, we'll have other things. But for the moment, this is what we have. And it's amazing that we having already vaccines and monoclonal antibodies. Really is, we've been able to develop this incredibly fast. And this happened thanks to 2 things. One is technology, and one is the investment the public sector has been doing. So I'll be talking now how we made what I consider a miracle to get vaccines and monoclonal antibody in less than 1 year. Let's start with the technologies. This slide tries to summarize in one slide all the technologies we've been using to make vaccines since Jenner and smallpox. Well, for 2 centuries, up to 1930, maybe also 1960, to make vaccines, we use a very empirical approach. We will take viruses, bacteria, parasites, we'll kill them and inject them, or we'll attenuate them, or we'll purify something out of them. But basically, in order to make vaccine, we needed the bacteria and the viruses. Then we started new waves of technology like recombinant DNA, glycoconjugation, genomics, and so on. And every wave of technology allowed us to conquer new diseases. And today, basically, what I see is an explosion of new technology. And there's so many technologies are really helping us. And my experience that 5 years ago, we were not able to do the things we can do today. And I believe that in 5 years, we'll be able to do things that today we cannot even dream. Now, going back to the pandemic and COVID-19 vaccines, there have been 4 technologies that have been fundamental to make vaccines so fast. The first one is what I call internet-based vaccines. The second one is the ability to use the structure, molecular structure of proteins and antigens to design vaccines. The third one is the synthetic biology part, including the RNA vaccines. And the fourth one, the ability to use adjuvants. Now, these top 4 technologies really allowed us to go very fast. The revolution that I think people have seen has been the availability of RNA vaccines, and we believe they are new. But this slide is basically to tell you that, RNA vaccines, the first time people started to work on them was 1993. I was working in 2008 on RNA vaccines. And we were already working on them in 2012, 2013, and so on. But to bring a new technology to a commercial phase takes a long time. And RNA vaccines were going to become products in 7-10 years from now without the pandemic. And the reason is that these vaccines are not yet completely mature from the industrial point of view. For instance, they need to be stored at -80. They are not really the formulation is not perfect, but somehow the need of vaccines from the pandemic really allowed us to go fast and to accelerate these things. So today we do have RNA vaccines, and we know they work well. Now, in order to understand why we went so fast, I'll tell you a story. Back in let's say 2009, when the first pandemic came, the influenza pandemic came, basically to make a vaccine, we had to take the virus from China, bring the virus to CDC, United States. They will grow the virus, and they will basically put the virus in and manipulate, and then give it to the vaccine manufacturers. And vaccine manufacturers 6-8 months later could start to make a vaccine. That thing changed completely on the Easter day of 2013. At that time, I had laboratories in Boston, and on the Easter day, the Chinese put on the internet the sequence of the influenza virus, which was H7N9, that was killed 3 people in China and had all the properties to become a pandemic vaccine, a pandemic strain. On Monday, Craig Venter was collaborating with me, was in San Diego in California, used the sequence from the internet and made 2 synthetic genes. And then on Monday night, he sent those 2 synthetic genes by express mail to our laboratory in Boston. On Tuesday morning, we started using those 2 synthetic genes to make 2 types of vaccines. One was an RNA vaccine, and the other one was a new virus, a synthetic virus, that was able to make a classical vaccine. Amazingly, in 7 days, actually in 6 days, we had both vaccines. It was the first time that basically, instead of shipping the virus across the continents or things like that, we used, to make a vaccine, we used information that had been teleported through the internet, made synthetic genes, and instead of spending several months to grow the virus, in 1 week we had vaccines. Now, that was the first time that vaccines could be made in 1 week, starting from the information. And in 2013, probably the only ones that could do that were our laboratories in collaboration with Craig Venter. But obviously, when in 2020, on January 10, the Chinese put on the internet the sequence of the coronavirus, there were hundreds of laboratories worldwide that could do what we did in 2013. So, from my point of view, this transition changed completely the way we do vaccines. Before, we used to do what I call analogic vaccines. Basically, where to make a vaccine, you need the virus, you need the bacteria, you need the parasite, you need really to grow these microorganisms. And that's how we've been making vaccines so far. Today, we are making what I call digital vaccines. Basically, you don't need the virus, the bacteria. You need information about their genome. That you don't need to send the virus across the globe. You just put the information in the internet, and that teleports the information. And then you build a synthetic gene in any place of the world, and you use that synthetic gene to make a vaccine. So that's the technology. Now let's talk a little bit about the other essential part which allowed to make vaccines so rapidly. That's the investment from the public sector. The United States put more than 10 billion on the table. Europe may put some billions. UK and Canada put other money. Why is that important? Well, to understand that, you need to look down here. These are the stages that usually we make to make a vaccine. To start to make a vaccine, you start with the discovery, which is where you do the science of the discovery of the vaccine. Once you discover a vaccine, you have a proof of concept in the lab that the vaccine works. You start what we call early development. Early development is industrialization, scale up, phase 1 clinical trial, phase 2 clinical trials. Once you have done that, you have a proof of concept in the clinic. Then you can move into the last phase, which is basically you build a factory, you make larger scale production, you do phase 3 clinical trials, and you submit all these things for registration. All these things more or less cost 1 billion from beginning to the end. And the cost is 10% at the beginning, then another 20%, and the large part is 70% at the end. So you will never build a factory unless everything is in industry. You basically, you do this, and only when this is successful, you move into this, and only when this is successful, you do the third one. This way, we manage the financial risk, because we only make investment if things work. Now, what happened for the pandemic during the pandemic response? Well, during the pandemic response, basically the governments, mostly the investment of the United States, they came, they say, well, if you make a vaccine doing first discovery, then phase 1, then phase 2, then phase 3, it's going to take you 10, 20 years to make this vaccine. And I understand you do this because you don't want to risk too much money. But here's the money. And they gave to most of the companies, the large vaccine companies, at least 1-2 billion each. And they said, I want you to do these things in parallel. Here's the money. Don't worry about the money. Me, as the government, I'm going to take the financial risk. You do everything in parallel. And if it doesn't work, I throw away the money. But if that's work, I'm going to get the vaccine much faster. So that's what happened. As soon as the discovery was done, phase 1 was started. As soon as we had the data that phase 1 was safe, we started phase 2. As soon as we knew that which was the right dose, we started phase 3. And basically, in 10 months, we have been able to make vaccines. One important message here is that, there are a lot of people say, well, you developed vaccines in 10 months. So since you went fast, I'm sure that you took a risk and we are not sure about the safety of these vaccines. And I think it's very important to understand that, you see, we did not skip any of the phases that usually we do to make vaccines. We did them all, but we did them in parallel instead of doing sequentially. So these vaccines have been licensed, have gone through all the steps that are necessary to establish safety and efficacy of vaccines. So basically, we are sure they're safe and efficacious, and we should be confident about them. We did take a risk, but the risk was on the money, not on the safety and efficacy. I think this is a question that people ask very often. It's important that we understand the process which has been followed. So which of the vaccines have been made? Well, using the process I said before, the January 10, 2020, the Chinese put on the internet a sequence. The sequence teleported. 300 labs worldwide start to make synthetic genes. And then with the synthetic genes, 3 types of vaccines were made. One, the fastest one, basically you take the synthetic gene, you transcribe, and in vitro, and you make a vaccine, completely synthetic. This is the fastest one. With Moderna, went into the clinic in 66 days, never done before. The other way to use the synthetic gene was to put the gene and splice it into one viral vector. Most typical are adenoviruses, human adenovirus, chimp adenovirus, gorilla adenovirus, but also measles vaccines and others. This takes a little bit longer because you have to splice the gene into the vector and then grow the virus and then use the virus as a vaccine. And this one takes a little bit longer, but AstraZeneca, or Oxford at the time, was able to go into the clinic in 3 months. Then there is the one more traditional, the one that we did, which is basically you take the synthetic gene, you use that synthetic gene to engineer a cell line, which can be mammalian, can be plant cell line, can be insect cell line, and then you grow the cell line to express the protein, the famous spike protein, which is the antigen to make a vaccine. Then you purify the spike protein, you combine with an adjuvant, and then you do the vaccine. This is a more classical vaccine and takes longer to get to the clinic, but now all these vaccines are in the clinic. How they look like? Well, we know they've been doing a lot of trials, and this slide tries to summarize all the vaccines, all the major vaccines, and how they look like. In order to understand them, you need to look at this blue arrow. This blue arrow gives an idea of the levels of antibodies against the spike protein in people that are convalescent from the disease. Since the level of antibodies in these people are supposed to give protection, whatever is above all this blue line should be efficacious as a vaccine. And as you can see, all the vaccines, the one made by viral vector, the ones made by RNA, the one by the protein plus adjuvant, they all are above this line. So the prediction was that all vaccines should be efficacious. Obviously, the level of antibodies induced by viral vectors is much lower than the one induced by RNA, and which is lower than the one induced by proteins plus adjuvants. That's what we learned from the phase 1-2 trials. Today, we also have the data from the efficacy trials, And we know that the vaccines from Moderna, from Pfizer, from Novavax have 95% efficacy. So these are incredibly good. I mean, these ones, they have lower antibody titers, also have lower efficacy, goes from 60 to 90%. So these are the vaccines that we have. They seem to, they all work, and they have, these ones appear to have incredibly high efficacy. This one have a good efficacy, not perfect, but very good efficacy. The important thing is to remember, this is efficacy from infection. All these vaccines, even the down here, basically give more than 90% efficacy from severe disease, from hospitalization, from death. So all these vaccines are very, very good. Now, we were very happy at the end of 2020 that we had all these vaccines coming. But at some point, we started to see this virus changing. The first change happened early 2020, was not really a big thing. Then we had the memes in Denmark. We had virus with several changes. Then we have variant in Brazil. And then we have the one in the UK, and then in South Africa, and then in Japan. And today there is a variant in New York, a variant in California, variants coming up in Italy. And the new question is that, will the vaccines that we are using going to cover this virus that is changing? And the answer is that probably yes, but not so well. In fact, the Moderna and Pfizer vaccines, I mean, they still cover the South African variant, but the antibody levels are approximately 12-fold less. So the vaccines against the South African variant are not that good. On top of that, we know that in terms of efficacy, the Novavax vaccine goes from 96% against the wild type virus to 60% in South Africa. And the Johnson & Johnson vaccine goes from almost 90% to 60%. So there is a drop in efficacy against the South African variant. And for this reason, already many companies are already working on second generation vaccines that should be able to cover completely also these things. Those vaccines will be available by the end of the year. So I think we should be confident that we'll get vaccines. Vaccines that will be able to cover also the variants. It's amazing that this virus basically is able to escape immunity. And we have seen that in the field with the variants, but we can reproduce that in the lab. In our laboratory, we put the virus in with a serum of a strong patient. I mean, that patient had very strong antibodies. And we saw that for 40 days, the virus did not change, but at some point started to escape partially. And then by 80, 90 days, accumulated mutations, and finally was able to fully escape immunity. So this virus has surprised us already a couple of times. And we'll make good vaccines, going to take care of it. But we should never relax, and we should continue to watch this virus. So I guess this is what I wanted to say about vaccines. Now I'm going to move to the other part of my talk, which is about passive immunization and human monoclonal antibodies. Passive immunization is nothing new. I mean, the first Nobel Prize, Emil von Behring, was given the Nobel Prize because he had discovered the serum against diphtheria in 1890. And that serum was able to save the lives of people. And that's why he got the Nobel Prize. During the past century, we have been using sera from animals and for humans to treat a lot of disease, for prevention. But today, basically, the new version of sera and passive immunization are human monoclonal antibodies. Now, human monoclonal antibodies are not new. During the last 20 years, there have been more than 100 products that have been licensed by FDA, the European Medicinal Agency, containing human monoclonal antibodies, made by human monoclonal antibodies. And these actually are the top sellers in the pharmaceutical industry. 7 of the 10 top sellers today are human monoclonal antibodies. But they're not for infectious diseases. They are used for cancer, for inflammatory diseases, from autoimmunity. Why they're not, we don't have many human monoclonal antibodies for infectious diseases? Well, there are 2 reasons. One is that in this field, in the field of cancer and inflammatory diseases, people pay, very expensive treatments because people are desperate and they can pay a lot. For infectious diseases, usually prices are much lower, so there's been little investment from pharmaceutical industry. That's one reason. But the other reason is that the technology was not there. Here, I show you several monoclonal antibodies against HIV. In 1994, the best we could do was a monoclonal antibody that was very weak, was not doing very much in vitro, in vivo was not doing anything. But then the technology improved. 10 years later, we were able to make human monoclonal antibodies that were 10 times more potent. Later, we were able to make human monoclonal antibodies that were 100 times more potent. And today, we can make human monoclonal antibodies that are 1,000 times more potent than what we were able to do 30 years ago. Indeed, a few months ago, the human monoclonal antibodies have been approved by FDA for the Ebola. And this is the first drug that we have been able to make against Ebola. So they start to be used in infectious diseases, but there are not many. So 1 year ago, when the pandemic came, we decided we wanted to make immediately very potent human monoclonal antibodies that which will be with a technology that will make extremely potent from the very beginning. Why we wanted very potent? Well, here tries to give you an idea. If you have an antibody with low potency, let's say neutralizes the virus 500 nanograms per ml, a therapeutic dose will be 5 grams. That will cost a lot. And the only way to deliver that is by long intravenous infusion. It can only be done in the hospital. However, if you have something which is 50 or 100 times more potent, like what we call second generation, are able to neutralize the virus 10 nanograms per ml. Now, 0.1 gram or 100 milligrams are sufficient as a therapeutic dose. And now you can give the antibody by injection in the doctor's office. You don't need to go in the hospital. And the price to manufacture is going to be much lower, obviously. So that's what we had in mind 1 year ago, and we started working on it. We made an agreement with Istituto Spallanzani in Rome and the University of Siena, the hospital of Siena, basically, to get blood from people that were convalescent from the disease. We took the blood, prepared PBNCs, and then we sorted the B cells from their blood. And for the cells, the B cells which were recognizing the spike protein of the virus. And then we put them 1 B cell per well. And then we looked for which ones, whether we're making antibodies that will recognize the spike protein. And here what we got. We got more than 4,000 memory B cells. You see the red ones. Each one is a memory B cell. That basically would recognize the spike protein. But then we wanted to find the ones which were extremely, making antibodies extremely potent. So the first thing we asked which of these was going to produce antibodies, was neutralizing or competing with the attachment of the virus to the cells. And so we had much lower quantities of cells that produce antibodies with this function. Then we asked which of these antibodies was able to neutralize the virus. And we found out of the 277 cells, we found only 10% of them, 453, that were able to neutralize the virus. And the majority of these were pretty weak neutralized. They needed at least 500 nanograms to neutralize. Some of them were better, but the ones we really wanted were the ones who were extremely potent. They will neutralize the virus at 10 nanograms or less per ml. We selected the 3 ones that are, you see, indicated by the arrows, and we started working on that. And we figured out that basically this is the cryo-electron microscopy of the spike protein, and this is the cryo-electron microscopy our antibody bound to it. And we found that basically the most potent antibodies were the ones that basically bind the receptor binding domain, which is this part, at the tip. Then if you go in this region, it's called S1, basically you get still potent antibodies, but less potent. If you go down here, you get less potency. If you go down here, which is the S2, you get even less potent antibodies. He basically took this antibody we industrialized, and we asked whether we'll protect animals from infection. And here is a prevention. Basically what we do, we took hamsters, which are a good model for this. We gave them the antibody on day 0. Then 24 hours later, we gave them the virus. And then we see if you, in the red line, if you don't give the antibody, the hamsters lose weight, lose weight, lose weight. If you give an antibody against influenza, which you should not protect, dotted line, you give the hamster lose weight. But if you give them the antibody at different doses, 4 milligrams per ml, 1 milligrams, or 0.25 milligrams, basically the hamster lose a little bit of weight, but then recover and stay well. Importantly, by day 3, the virus in the lung was completely gone, was no more. So basically, these antibodies work very well to prevent the disease. What about therapy? Well, in the therapy thing, we did a similar thing. We basically gave first the virus, and 24 hours later, we gave the antibody, and we observed similar things, no antibodies in the lung. So basically, we found that in animal models, these antibodies were actually working very well. Then, this was the work we did a year ago. Basically, by June 2020, all this work in the lab was done. And then at that point, we started making the industrialization of this work. We started to make a cell line that will manufacture this antibody in large scale. A cell bank will produce GMP lot in large scale fermenters. We'll fill them, and we start a clinical trial, which is basically still going on right now. So this antibody now is in clinical trial. While we're doing this work, the variants came, so we had to ask the question of whether our antibody will be able to cover the variants, and we found that our antibody covers well the wild type, the initial variant, the UK variant, but also the variants from South Africa and from Brazil. And this is very important because many other groups basically came out with antibodies which basically were completely useless against the variants from South Africa and Brazil. So our antibody for the moment works very well. Now, how do we know they work? There have been, in these months, actually, 2 reports from other groups that already finished the phase 3 trials and basically have shown that they have 87% efficacy against hospitalization and death, or 85% efficacy. So basically, we know that these antibodies, if given to people that are positive to the swab, they will clear the virus and very quickly, and they will not go into severe disease. They do not go to the hospital. They don't go to intensive care. They don't die. So the antibodies are extremely important for people that are infected, because once you're infected, you cannot use a vaccine, so you need a therapy. And these antibodies are a very good therapy. Now, that's the end of my presentation. And now I want to go back to the title. And the title basically says we want to get back our liberty. And I selected here the Statue of Liberty to conclude my talk. And what's the reason for that? Well, the reason is that basically this pandemic has taken away a lot of our freedom. Our freedom to go out, to walk, to work, to travel, to meet friends, to visit relatives, but also to go to theater, to go to cinema, to go to soccer, to play sport, everything. We desperately need our freedom back. And I believe, I'm confident that the 2 tools that science provides to us during this period will be able to give us back our freedom. And with that, I think I'm concluded. I just wanted to show the people that developed the monoclonal antibody that I described, and the collaborators in the world that basically helped us to fully characterize, do the animal trials, do the structure of the antibodies, and all these kind of things. With that, I would like to thank you for your attention.
Thank you very much for this beautiful and very illuminating presentation. I took the lead before even Antonino.
Yes, thank you, Rino, for your beautiful presentation. I'm sure that there are questions, and I would like to ask everyone who has a question to drop a line in the chat or to raise hands, but I hope I can see the hands. So please drop a line in the chat. Okay. So, yes, Augusto, fire your first question, please.
Things that I wanted to ask, a couple of things that you mentioned in your talk. At least you skimmed around them. Now, there's the issue of the modified RNA vaccines and the less innovative ones like AstraZeneca. And my concern was your opinion on why Europe fell into that direction. I see a lot of politics and much less science guiding the choice, and also the issue of saving money, which in this at this stage doesn't seem to be the most important idea, since if you save money one way and you don't open because the vaccine is less effective, or in any case you get delays like they're getting, then the problem presents itself in a serious fashion. Thank you.
Well, clearly what I showed is the science to make the vaccines. Then the problem we are basically facing right now is that there are not enough vaccines. And that is not unexpected. Because obviously to make vaccines, you need factories. You need plants. You need industrial things. And we didn't have them ready. So the science has moved very fast. But making industrial plants to make vaccines really takes time. And so basically the reason why we don't have so many vaccines is because the capacity of the production, the global production is not sufficient. It's catching up. We'll eventually going to get there, but it's going to take a while. So that's the main reason why we don't have enough vaccines. So I think the companies, right now in the media, they're talking a lot about AstraZeneca is not providing the vaccines, the others are not giving the vaccines. I think the reason they are not giving is because they don't have them. From my point of view, I consider a miracle that we have vaccines at this point. 1 year ago, when people were asking me how long it's going to take to make a vaccine, I was saying, well, usually it takes 10, 15 years. Now we're in a pandemic, we'll move fast. Maybe if you are very lucky, it's going to be 18 months, maybe 3 years. Instead, we got vaccines in 10 months. So we should be pretty happy about it. Obviously, we need to try to vaccinate as many people as possible, but I believe that the crisis that we see for the absence of vaccines is because it's very difficult to make them in large scale. We are not asking for 1 million, we are asking for hundreds of millions of vaccines. So I think that's the thing. Then the other question is that obviously not all vaccines have similar efficacy against the infection. We know the famous or infamous AstraZeneca has 60%, the RNA vaccines and the protein-based vaccines are 95%. But we also should remember that all vaccines, including the AstraZeneca, they have more than 90% against severe disease, against hospitalization, and against mortality. So if we understand that the things that we fear the most today is the fact that people go to intensive care, they collapse the hospital and they die, all vaccines are able to prevent that. So that's why they're all recommended.
Thank you. This final sentence is a very, very important message. Everything was important, but this one is thank you. Next question is from Alessandra Toncelli. I will read it. How long does the immunization last after vaccination? Good question.
The answer is that we don't know because the vaccine, which is very recent, we know that the first 2 doses will protect for a few months. Depends on the vaccines. I think maybe 6 months, maybe more. But then at some point, we'll need to give us, to get long-lasting protection, we will need another boost, a third dose, I think. And then after the third dose, things will last long. We already have some evidence that already published that people that have been infected and then they got a vaccine, 1 dose is sufficient to give extremely high titers, like 10-fold more than after normal vaccination. So when you get those titers, it's going to last very long. So that's why I believe at some point we'll need to give a third dose.
Thank you. Next question is Julia Freire. She writes, thanks for the very clear seminar. Can we say that the advantage of monoclonal antibodies over patient-donated serum is above all a question of affinity for the antigen?
I think yes, definitely. One way, when people very often ask, what's the difference between monoclonal antibodies and plasma? The plasma was not that successful. Why should monoclonal antibodies work? And the best answer to that is an analogy that was actually I got from one of the interviews of Sergio Brignani, and he basically said the monoclonal antibodies is like the distillation of the plasma. Basically, you take the best of the plasma and you distill it, like you do with distillation from the grape wine to make grappa. And so basically, the monoclonal antibodies take the best antibodies which are present or in the plasma, and they make a lot of it. So they're consistent, they have high titers, they're very good. While the plasma, the problem with the plasma is that it's very difficult to find plasma with high titer. And so that's why most of the things fail.
Thank you. I have a question myself. In February 2020, you mentioned that you got your first monoclonals in 3 months, basically, which was a remarkable, really, achievement. And in February 2020, on bioRxiv, the first 2 reports were posted on the first anti-spike human antibodies. And we were discussing this in the lab, and we were saying, this is absolutely impossible from a really practical point of view. And then you look into it, and you saw that these first reported antibodies were antibodies against the virus of SARS-CoV, the 2003.
Yes.
And those happened to cross-react. Well, not happened. There is a deep reason for this. So my question now is a general one. That was probably a sliding door. If we had had in the freezer monoclonal antibodies clinically tested against that virus, we could have used them immediately in March or April 2020. So this is a sliding door and is a lesson for the future, probably, about preparedness.
Absolutely. So the antibody you are talking about is the one developed by Antonio Lanzavecchia.
Yes.
And he and I collaborated back in 2002 with the first SARS SARS outbreak. At that time, I was working on making vaccines for SARS. I had all the tools to make, to basically do neutralization, had to detect the antibodies, all these kind of things. And Antonio was he had the tools to clone B cells, human B cells. Up to that point, it was impossible. He was the first one to do it. And then we collaborated. He got a patient at the hospital Sacco in Milan from SARS, and he made the antibodies. I provided tools, and we published in Nature Medicine in 2005 an antibody. Then in 2014, he got back to the same patient because in 2014, in the meantime, MERS, another coronavirus, had appeared in South Africa, in Saudi Arabia. So after that, he basically got back to the same patient in 2002 and got blood from that patient again and looked for antibodies from monoclonal antibodies that will cross-react against SARS and MERS. And he published that at that time. And then as soon as SARS-CoV-2 came, he went back and found that was cross-reacting with this as well. So absolutely, I mean, if we had developed that antibody that we had from 2014, probably we had the tool to stop this pandemic at the very beginning.
Yes, and a very important message for the future.
Absolutely.
Next question, Emanuela Colla. Can monoclonal antibodies against COVID be used for any patient, even for late stage of the disease?
So the antibodies that have been licensed so far for emergency use are only approved for people that are not in the hospital and they are not under oxygen yet. That's where they work well, in people that at the beginning of the infection, because the antibody basically resolves the infection and people don't get sick. There have been trials with those antibodies in people that are in hospital, and so far that did not work. So in severe patients, probably it's very likely that the virus has already done so much damage in the lungs and the body that it's too late for the antibodies to work.
Thank you. We have at the moment at least 2 other questions. If you have patience, Roberto Contino Thank you for the beautiful seminar. What are the steps, in your opinion, that we as Italy and at a more global level should take to be prepared for the next pandemic?
Well, you know, I think the lesson is pretty hard. What we learned is that one infectious disease can really put on the knee one economy, take away our freedom, and kill a lot of people. Now, if you want to avoid that, I think we have shown that we have the tools, the science, and the tools to be prepared and to try to prevent these things. So what we need is investment. We need an investment as an insurance that basically that we will be ready and for anything that is going to come. And it's not new. I mean, I've been saying this since 2002. But people listen, they say, well, but you know, when you are well, you never think that nobody thought that something like this could happen again. And so nobody invested so far. So it's a question, I mean, if we consider the economic loss that we are having globally, I mean, if we had invested like 10 billion a year globally to prevent something, I mean, will be a very good investment. We never did it. Hopefully this time we'll learn a lesson.
Augusto Stagnotti, do you have an opinion on the Russian vaccine?
Well, the Russian vaccine is, in theory, is a good vaccine because it's a viral vector and is basically uses two adenoviruses. One, which is the same one used by J&J, which is an adeno 26, and the other one is adeno 5, which is used by some of the Chinese. So it's more complex than the others because to make one vaccine, you need two viruses. So you need to basically produce two vaccines to make one. But in theory, it's better than the other viral vectors because the other viral vectors, what they do, they induce antibodies not only against the coronavirus, but also against the vector. So the second dose of viral vectors usually is not that useful. While if you change the vector, like the Russian do, the response to the second dose is good. Now, the problem with the Russian vaccine is that all the trials have been performed outside of any control of a Western regulatory agency. So basically, I think now the European Medicinal Agency is looking at those data, and I'm confident that if they say yes, means that the data are okay. I haven't seen the data, so I cannot comment on that.
Thank you. Emanuela Colla, still on the COVID vaccine. Since COVID vaccines have different efficacy against different variants, would you recommend a person get vaccinated with multiple vaccines? I add, if they were available, AstraZeneca plus J&J plus Pfizer. And then she thanks you very much for your beautiful presentation and taking the time to answer our question.
Well, thank you for listening. So the answer is that we talk about different vaccines, but indeed they are all the same vaccine. They're all made by the spike protein. It's just a different way to deliver the same vaccine. So fundamentally, I believe that all these vaccines are interchangeable. I mean, I would have no problem to use AstraZeneca for priming, I don't know, another one for boosting. I mean, really, they're all the same. So I think we should have more flexibility on these things.
Simonetta Lisi, are there trials of combination/cocktails of different monoclonal antibodies, or are they to be used as single drug?
Some of the monoclonal antibodies are cocktails. But the variants have shown that cocktails may not, I mean, the theory is that if you have a cocktail of 2 antibodies, for the virus is more difficult to escape, which is true in theory. But then, for instance, some of the cocktails had 2 antibodies that both of them are knocked out by the South African variant, or one of the 2 is knocked out by the South African variant. So I think usually cocktails of antibodies are better, but it's more important to have the right antibody that the virus cannot escape.
Thank you. Very clear. I don't see other written questions. If there is anyone who would like to ask something to Professor Rappuoli, he's still here to answer. And in the meantime, I really thank you, Rino, very, very much for a great presentation, clarity, and also for your answers in the questions that are burning questions from all of us. And thank you for the work that you're doing. I don't see other questions coming, so I would like to thank you very much. And really, I would have liked to a warm applause in Sala Azzurra, Scuola Normale, and we hope that you can come back again to Scuola Normale. We are not far, so Tuscany is a hub of the world at the moment in terms of vaccines and monoclonal antibodies, and so please come and see us again, and thank you very much again for your work.
Well, thank you all, and definitely as soon as you
very much.
I'll come and see you.
Thank you.
Thank you, and thank you to everyone. Bye-bye. Arrivederci, Rino.